For centuries, the nature of light has captivated and puzzled scientists. Is light a wave, flowing through space like ripples on a pond? Or is it a stream of particles, tiny packets of energy hurtling through the cosmos? This fundamental question sparked a debate that would shape the course of scientific thought. Early thinkers, observing how light bends around objects and spreads out from sources, leaned towards the wave theory. The renowned Isaac Newton, however, championed the particle theory. He envisioned light as a shower of minuscule corpuscles, explaining its straight-line travel and reflection. The debate raged on, each side presenting compelling evidence. It seemed an impasse, a puzzle with no solution. Little did they know that the answer lay not in choosing one side over the other, but in embracing the bizarre truth. Light is both wave and particle. This profound realization marked the dawn of a new era in physics, one that would challenge our very understanding of reality itself. It is a journey into the heart of the quantum world, where the familiar rules of classical physics break down and light reveals its true enigmatic nature. The quest to understand light reads like a who's who of scientific giants. Each contributed a vital piece to the puzzle, paving the way for our current understanding. Isaac Newton, with his groundbreaking work on optics, laid the foundation for our understanding of light's behavior. His meticulous experiments revealed the spectrum of colors hidden within white light, hinting at the complexity that lay beneath the surface. James Clerk Maxwell, a brilliant Scottish physicist, unified electricity and magnetism with his elegant equations. These equations predicted the existence of electromagnetic waves, ripples in the fabric of space-time that travel at the speed of light. This discovery suggested a profound link between light, electricity, and magnetism. Enter Albert Einstein, a revolutionary thinker who would reshape our understanding of space, time, and gravity. Einstein proposed that light isn't just a wave, it also exists as discrete packets of energy called photons. This audacious idea, known as the photoelectric effect, earned him the Nobel Prize and provided crucial evidence for the dual nature of light. These pioneers, each with their unique perspectives and groundbreaking discoveries, set the stage for the quantum revolution. Their work challenged established notions and opened up a new realm of possibilities, ultimately leading us to the astounding world of quantum mechanics. The concept of wave-particle duality is one of the most mind-boggling ideas in modern physics. It states that light, along with other fundamental entities like electrons, possess both wave-like and particle-like properties. This isn't a matter of light switching between the two, it embodies both aspects simultaneously. Imagine a serene lake on a still day. A pebble dropped into the water creates ripples that spread outward, embodying the wave-like nature of light. Now imagine a beam of sunlight striking a solar panel, each photon like a tiny particle transferring its energy to generate electricity. This duality is not a limitation of our understanding or a flaw in our instruments. It is a fundamental aspect of the quantum world where the classical distinctions between waves and particles blur. Light, in its elegant dance between these two states, reveals the profound strangeness and beauty of the quantum realm. Grasping this duality is key to understanding the behavior of light and matter at the smallest scales. It forms the bedrock of quantum mechanics, a theory that has revolutionized our understanding of the universe and paved the way for groundbreaking technologies. The enigmatic nature of light's wave-particle duality is perhaps best illustrated by the double-slit experiment. This simple yet profound experiment, a cornerstone of quantum mechanics, reveals the bizarre behavior of light and challenges our classical intuitions. Imagine shining a beam of light at a barrier with two closely spaced slits. Behind the barrier lies a screen that captures the light passing through the slits. If light were purely a wave, we'd expect to see an interference pattern on the screen, a series of bright and dark bands caused by the waves overlapping and cancelling each other out. Astonishingly, that's precisely what happens. Even more surprising, the interference pattern persists even when we fire individual photons one at a time towards the slits. This implies that a single photon somehow interacts with both slits simultaneously, as if interfering with itself. This mind-boggling behavior can only be explained if we accept that light embodies both wave and particle characteristics. The double-slit experiment, therefore, provides compelling evidence for the quantum nature of light and highlights the limitations of our classical worldview. Section 5. Embracing uncertainty, Heisenberg's principle. The quantum world is a realm shrouded in uncertainty, and at its heart lies Heisenberg's uncertainty principle. This groundbreaking principle, formulated by German physicist Werner Heisenberg, states that we cannot simultaneously know both the position and momentum of a particle, such as a photon, with perfect accuracy. Imagine trying to pinpoint the location of a wave on the ocean. The more precisely you define its position, the less certain you become about its wavelength, which dictates its momentum. This inherent fuzziness isn't due to limitations in our measurement tools, but a fundamental aspect of the quantum realm. Heisenberg's principle has profound implications for our understanding of the universe. It tells us that at the quantum level, certainty gives way to probability. We can only predict the likelihood of finding a particle in a particular state, not its exact location or momentum. This inherent uncertainty, far from being a nuisance, is actually what makes the quantum world so fascinating and dynamic. It is this uncertainty that allows for quantum phenomena like tunneling, superposition, and entanglement, which have revolutionized fields like computing, cryptography, and our understanding of the very fabric of reality. Section 6. Quantum mechanics, a revolution in understanding reality. The discoveries of wave-particle duality and the uncertainty principle marked a turning point in physics. They forced scientists to abandon their classical intuitions and embrace a radically new framework for understanding the universe at its most fundamental level: quantum mechanics. Quantum mechanics, a mathematical framework for describing the behavior of matter and energy at the atomic and subatomic levels, has revolutionized our understanding of the universe. It is a probabilistic theory, meaning that it deals with probabilities rather than certainties. This new way of thinking has had profound implications for our understanding of the universe. It has led to the development of technologies like lasers, transistors, and nuclear energy, and it continues to drive innovation in fields like quantum computing and nanotechnology. Quantum mechanics isn't just a theory about the very small, it's a profound shift in our understanding of reality itself. It challenges our classical notions of causality, determinism, and the nature of observation, forcing us to reconsider what it means to truly understand the universe. Section 7. Visualizing the invisible and analogies for the quantum world. The quantum world, with its counterintuitive concepts and bizarre phenomena, can be notoriously difficult to grasp. Fortunately, analogies can help us visualize these abstract ideas and build a more intuitive understanding of this strange and wonderful realm. Imagine a spinning coin constantly flipping between heads and tails. This represents a quantum object existing in a state of superposition, a blend of multiple states at once. Only upon observation does the coin collapse into a definite state, either heads or tails. Think of a group of synchronized swimmers, their movements mirroring each other perfectly. This illustrates the concept of entanglement, where two or more quantum objects become linked, their fates intertwined, regardless of the distance separating them. These analogies, while imperfect, provide a foothold into the abstract world of quantum mechanics. They help us bridge the gap between our everyday experiences and the counterintuitive yet fascinating reality that governs the universe at its most fundamental level. Section 8. From Theory to Technology, Quantum Applications in Our Lives. Quantum mechanics, once a realm of theoretical physics, has rapidly transitioned from the laboratory to our everyday lives. Its principles underpin a vast array of technologies, transforming the way we communicate, generate energy, and process information. Solar panels, for instance, rely on the photoelectric effect, Einstein's Nobel Prize-winning discovery to convert sunlight into electricity. Each photon of light knocks an electron loose from a semiconductor material, generating a flow of current that powers our homes and devices. Lasers, ubiquitous in telecommunications, barcode scanners, and medical devices, exploit the quantum property of light amplification. By stimulating atoms to emit photons in a synchronized manner, lasers produce highly focused beams of light with remarkable precision and intensity. Quantum computing, still in its nascent stages, holds the potential to revolutionize fields like medicine, materials science and artificial intelligence. By harnessing the power of superposition and entanglement, quantum computers could tackle problems deemed intractable for even the most powerful classical computers. Section 9. The Enigma of Light. A journey continues. The journey to understand light has been a long and winding one, marked by brilliant minds, groundbreaking discoveries, and a profound shift in our understanding of the universe. From the wave-particle debate to the mind-boggling world of quantum mechanics, light has revealed itself to be an entity of remarkable complexity and beauty. Yet, the story of light is far from over. While we have made incredible strides in unraveling its mysteries, many questions remain. How does light interact with gravity at the quantum level? What is the nature of the vacuum, the seemingly empty space that is teeming with quantum fluctuations? The pursuit of these answers continues to drive scientific exploration, pushing the boundaries of our knowledge and challenging us to reconsider what we thought we knew about the universe. Perhaps the most profound question of all remains, what really is light? This seemingly simple question, pondered by philosophers and physicists for centuries, leads us on a journey into the heart of quantum reality, a realm where the familiar rules of classical physics break down, and the true nature of light in all its enigmatic glory awaits to be fully unveiled.